Okay. So today I'm happy to introduce Antoine Tilloy. He's a French physicist. He did his work at there in France. He was working at for his degree at the École Polytechnique and École Normale Supérieure, and then he did a research intern at Harvard University. And was working also in Germany at the Max Planck Institute for Quantum Optics as a researcher, and has recently begun a position at the Paris School of Mines as an assistant professor. His interests are in quantum foundations, and particularly has done some nice work on the theory of quantum trajectories. And today's work, he'll be telling us about his research with our also member of the Institute for Quantum Studies, Howard Wiseman, talking about the link between non-Markovian models and de Broglie-Bohm theory. So Antoine, it's a pleasure to have you here. I give you the floor.
Okay, thanks a lot, Andrew, for the introduction. Yeah, I'm very happy to talk about this foundational results. So it's really, I warn you, it's in a way pure foundations today, foundations of quantum mechanics. It's work I did with Howard Wiseman actually a few years ago, but that took forever to write up. And historically, in fact, the idea is in an earlier paper, buried in an earlier paper by Howard Wiseman and Jay Gambetta. So I don't really have actually the paternity of this idea, to be fully honest with you here. And yeah, the objective of today is to compare two leading approaches to sort of realist foundations of quantum mechanics and see how surprisingly similar they are, even at the level of the equations, in a way that seems counterintuitive and almost wrong if you state the results too quickly. Okay, so let me start. I will first summarize the results so that you know if it's worth staying, and then if you feel it's not interesting, it's really, you can totally leave after these 2 slides. And then if you are interested, I will keep on for the rest of the talk to describe these results in more detail. So yeah, we have 2 realist reconstruction of quantum mechanics on the market. One is the de Broglie-Bohm approach, and the philosophy is quite simple. The wave function evolves unitarily according to the standard Schrödinger equation. And then you solve the measurement problem of the standard interpretation by adding particles that are guided by this wave function. And in a way, at the end of the day, the metaphysics of the world is just you have particles that move, and coarse graining these particle positions give rise to macroscopic stuff that is not superposed. Another approach, the second main approach, I would say, to this realistic single world foundation is objective collapse. And in that case, the wave function does not evolve unitarily. You add the small corrections to the Schrödinger equation that is designed carefully to kill macroscopic superpositions, but have very little impact on microscopic dynamics. And in such a picture, the real world, what you would say is real, is either the wave function itself or these collapse events, the flashes where the wave function collapses. I will say more about these models. So if you have completely different philosophies, this thing cannot possibly in any way be the same or even just similar. But it turns out that there is a connection, a weak inclusion and a strong inclusion. And I'd like to start by saying the weak inclusion that is in some sense trivial, even though it is often misunderstood, and a strong inclusion. But this one is difficult, so let me explain the weak inclusion. That should be simple. If you start from a reasonably generic collapse model on a certain system, so this modified Schrödinger equation, then you can always find a bus of oscillators and some carefully chosen unitary dynamics on this extended system plus bus, such that the 2 models, the collapse model and your standard quantum mechanics on the extended system, the 2 are empirically indistinguishable. So collapse model on the system is empirically equivalent with de Broglie-Bohm, and in fact, any other interpretation, Copenhagen, many worlds, or whatever, on the n-large system. This is a point that's very familiar for people used to work with BAS and open quantum systems, where at the end of the day, if you don't have access to measurement results, an unraveling is equivalent to the Lindblad evolution. This is for the Markovian case. Here, it's more general. It's for even non-Markovian evolution, non-Markovian collapse models. I would say this point is quite clear, it's quite easy, but that's not the main point I want to make. And usually my difficult part in such a presentation is having people understand that this is actually easy and that that's not the main point. The hard point, and the point that is really non-trivial and for which you really need Bohm and not just whatever interpretation, is to go to an inclusion that is not only at the empirical level, but even at the level of the basic objects of the theory. And you get it by taking the same BAS as before that gave the empirical equivalent, and you supplement the BAS oscillators with Bohmian positions, so with the standard Bohmian hidden variables. And then what you see is that the wave function of the collapse model, the stochastic wave function of the collapse model on your system is exactly, it's not approximately, it's exactly the de Broglie-Bohm wave function on the full extended system conditioned on the real-time evolving hidden variables. And then the collapse model noise has the same law as a linear function of the particle. So basically you can relate the distribution of the hidden variable of the oscillator to the noise that drives the collapse model. So it's a stronger equivalence. It's a sort of ontological equivalence at the level of the wave function itself, not just observables. The two models are the same. And this is the one that is really non-trivial and where you really need the specific Bohmian guiding law to match the two sides of the equality. Okay, so that is what I want to show today, to explain. But in the process, I think what is the most important is to explain what these collapse models are. So for those of you who are familiar with quantum trajectories occurring in the context of measurement, this is fairly easy technically. But I would be even simpler than that, just consider discrete models. Then explain why these models are strongly constrained and why you cannot make anything, why they have a lot of structure, a structure we will exploit. Then explain how modern collapse models are made. So these collapse models that are with colored noise that have no equivalent in the measurement, in the continuous measurement literature. And they are the one that we can Bohmianize. So the one that we can have, that we can make equivalent with a Bohmian theory on a dilated Hilbert space. I will just explain briefly how to do that and then discuss the implication. When we will reach the discussion, some slides will switch to French because I didn't have time to translate them in English because I gave this presentation in French a few weeks ago. And so, yeah, some side of the discussion will be only oral. I will still give them in French if you read French, but yeah, this part is, you will less prepare the discussion part. Okay, so of course, feel free to interrupt, to protest at everything I say at any time. Okay, that's how it should go. So let me first tell you the basic idea and the origin of this collapse model, starting from Ghirardi, Rimini, and Weber. Yeah, just a general philosophy and maybe some names in case you see it said differently in the literature. So this thing has many possible names. So when I say collapse models, I mean either objective, spontaneous, dynamical. Then you can replace collapse by reduction or model by program. You can do any combination of these words that refers to the same thing in the literature. So spontaneous, spontaneous collapse model, that's the thing. Dynamical reduction program, that's the thing. That's all the same thing, okay? And the idea is just you take the Schrödinger equation and you add a tiny nonlinear bit, which is this epsilon f psi. Here in your Schrödinger equation, it's the Hamiltonian is typically all there is. It's the standard model Hamiltonian or some non-relativistic approximation. And you would like to know if by doing this, you can solve the measurement problem, or at least don't have like macroscopic Schrödinger cats while not being falsified. This is very high talk, had no reason to be true or any good choice. I think the primary objective of these people was really to show that it's just possible. Okay, I wrote possible twice, sorry, but just possible. You want to see that it's doable. not necessarily that it's appealing or a good idea to do so. And the proposition of GRW was keep the standard Schrödinger evolution, but now assume that every infinitesimal amount of time dt with some probability lambda dt, every particle in the world can collapse around a certain point xf. So, and this, I say around a point because you have a certain Gaussian envelope. So randomly, a particle will collapse to something projected multiplied by this envelope and normalized with a probability given by the Born rule, so by this norm squared. So if you have an original wave function of say, a single particle, randomly, it can get collapsed into some narrow Gaussian. And so you have two parameters, the width of this Gaussian into which you are collapsed and the rate at which this kind of spontaneous jump can occur. Why the hell does it work? Why does it solve in any way the measurement problem? So if you take the initial, the historical proposal for the rate, it was 10⁻16 seconds, in which case an electron collapses every 300 million years. So basically you're never gonna see your single atom collapse in an experiment. However, a cat with 10⁻28 electron is localized almost instantly. Okay, so you have this amplification phenomenon that a very rare collapse on microscopic scales becomes very frequent on macroscopic scale, but a single collapse is sufficient in a large body to collapse everything. And in brief, you can even semi-rigorously derive the measurement postulate simply by applying this GRW dynamics to the measurement apparatus. So you forget about the measurement postulate, you can sort of derive it, I say semi-rigorously, in the same way we derive semi-rigorously in thermodynamics, the measurement postulate. And then when you have microscopic degrees of freedom, they never collapse because of their intrinsic collapsing dynamics of GRW, but they collapse when they are coupled to something macroscopic with a ton of degrees of freedom that has frequent collapses. And you get sort of, in a quantitative way, the split that Bohr himself envisioned. Okay, so that's sort of the basic of why it works. And then I'm not saying it's appealing, okay? I have a fairly actually personally negative opinion now on these models, but I think is the point we can grant that is on principle, it does work. And then what happens metaphysically? So why I insist on that is that now you don't have measurement results as the primitive in your theory. You have to find another primitive. And you have to say basically what is real, what is the world made of in this approach. And then you have basically three proposals on the market, either the wave function itself, which is now that the wave function doesn't do Schrödinger cats, now that it's well localized in space for macroscopic bodies, it sort of makes sense to take it real. But I should say it comes with an infinite literature of subtlety, so it's philosophically it creates problems. Or you can just project this wave function into real space, R3, instead of configuration space by taking the mass density, and this gives typically more sensible results, more sensible intuition, I would say, of what something real would be. Or you can even take the collapse events themselves as what's real. And then reality emerges as a sort of pointillist picture in space-time of all these punctual collapses that happen. And it was Bell's favorite option because it has nice, it has better invariance properties than the wave function itself. So it's easier to make the probability distribution of these flashes well-behaved and typically Lorentz invariant in some cases than it is to have the same for a collapsing wave function. Okay, so that's, we saw like the sort of the metaphysical content, what the theory says the world is made of, what tables and chairs are made of. And then the last thing is, what does it predict that is different from what we know? And then you have like sort of four main predictions that these models make. The first natural and expected one is that you have a loss of interference, that things make less of a strong interference pattern when they become very large, because they have a probability to collapse during the interference experiment. But it turns out this is a very weak signature, and that the stronger signatures are that matter heats up, even though very slowly, but energy is no longer conserved in this model. In fact, spontaneously, stuff gets hotter, but very slowly. Stuff also vibrates, and stuff also tends to emit X-rays spontaneously because of this collapse. Basically, when you have a collapse event, you can inject sufficient amount of energy that your electron will change of shell and emit X-ray. Okay, for the first one, a good test are the experiments of Marcus Arndt with macromolecules, but I should say they don't constrain so much the range. For the second one, matter heats up, you can look at my personal favorite, neutron stars. So neutron stars would shine extremely bright if the collapse parameters were taken to be large. And then for vibration, you have the mirrors of LISA Pathfinder. And actually, the best results are obtained from germanium crystals taken under the mountains in Italy, where basically collapse models predict they should emit radiation, and we don't see any radiation emitted from these crystals, as I would say everyone would expect. This gives a certain allowed diamond of parameters for these models that is not yet falsified. This is the white one. The blue and red ones are experimental falsification, either with X-ray or with gravitational wave detectors. And the lower one is philosophically unappealing, which means that, sure, you can have a collapse model with these parameters, but then this collapse model does nothing for you. So it doesn't collapse macroscopic superpositions sufficiently fast. And so at the end of the day, you recreate a many world picture effectively in this range of the diagram. Okay, so I think that was my sort of summary of the basics of collapse models. So of the GRW type, at least. So once you've seen such a weird model with these flashes and stuff, you can ask, okay, but we must be able to do things differently. It doesn't make any sense to take such stochastic weird equations. And so Steven Weinberg, back in the late 80s, tried to write a deterministic modification of the Schrödinger equation that would collapse macroscopic superpositions and do nothing for microscopic ones. But in fact, even a few months before, Gisin had understood that it was not possible, and that for whatever nonlinear deterministic modification of the Schrödinger equation, you can send signals faster than light or break the Born rule. And the idea is, if you have such a modification that is deterministic, it will generically, in fact, always break the empirical equivalence between statistical mixtures and entangled states. So in an EPR type situation, Alice and Bob make measurements, but the statistics, so you see, Bob cannot know on his local statistics whether or not Alice measured. Of course, when they come together, they see weird correlation, and that's Bell type correlations. But Bob cannot know if Alice measured because of this equivalence. And once you have a small nonlinearity, you can always distinguish locally whether or not Alice measured. And this allows Alice to send you signals faster than light. By simply choosing or not to measure, it's a bit, and you do it many times with many pairs shared, and you can set signals. So that's a no-go for this simple trick. Then you have to understand why models like GRW don't have that. And the answer from continuous measurement would be that they are simply equivalent to continuous measurement, and they are the unraveling of a legitimate master equation. But let's say we don't know that. Then the crucial point is that in practice, you can only ever measure frequencies. So like, let's say to simplify the expectation value of a projector, this is the kind of frequencies of occurrences that you will see in an experiment. But in addition, they are averaged over the jumps, over this stochasticity, because we don't have the only access we have to the stochasticity of the GRW model is through the state itself, which we measure. So we don't know it, so we can only average over it. And this average frequency, if you look at it, only depends as a result on the average of the state itself. And this is the density matrix. So all the falsifiable predictions of the model are in the density matrix, expectation value of ket psi bar psi. I'm not saying that everything, so for example, this row doesn't collapse, but it only decoheres. So I just say it's falsifiable prediction. Then of course the model says more than row. It tells us that the measurement problem is solved, for example, but it doesn't do more than that. The predictions don't go beyond that. And of course, the GRW dynamics is made in such a way that when you take expectation value, all the nonlinearity goes away and you are left with a Lindblad type equation, which is perfectly linear and perfectly legitimate and just cannot create weird stuff. Okay, so that's all of that is for the historical collapse models that were Markovian. And the point I want to make is about their extensions that are non-Markovian one. And this is where we lose all the intuition with continuous measurement, because there is no theory of non-Markovian continuous measurement that makes sense, at least for in real time. Okay, and then this slide is in French for some reason, but this is where you have to see, you cannot just take the presentations collapse people give of their model. You really have to see how the sausage is made. So you really have to enter into the detail of how these models are constructed, because they are highly counterintuitive. And it is because of some things that are hidden in them that we managed to do our mapping to Bohmian mechanics. Otherwise we couldn't. So that's important. And the questions that people ask, I think in the 2000 or so, was, okay, but what kind of, I should say very quickly, okay, why did they consider non-Markovian or a collapse model with colored noise? To make them harder to falsify, okay? Because otherwise we believe that Markovian collapse models will be falsified very soon, that the diamond will be closed. So let's say, okay, we can just smooth things and have a nonlinear term, but this now it's a very generic nonlinear term. There is no, not necessarily the noise is white. And in fact, it's still very, very constrained. If you want two things, basically that this equation reduces superposition in a certain basis, typically position. And second, if you want not that the dynamics is Lindblad, because it's no longer, that the average dynamics is Lindblad, it's no longer possible. But if you ask that it's completely positive trace preserving. And this is sort of necessary if you don't want to be attacked by Nicolas Gézin. Okay, so if you want these models to make sense, basically. Okay, so these are the constraints, and let me show you how people constructed them historically, and that's very complicated. So, I mean, that's good to have in mind, it's complicated. So you start by defining a linear collapse equation, a linear stochastic differential equation. This is a linear state. You have a Hamiltonian, which was the one you had before, and you add a noise term proportional to some operator. This is what would be the naive stochasticity. That's what you have in mind when you think, oh, I am adding I'm adding colored noise in the equation. But then you realize that if you want a completely positive trace preserving map, you have to add a correction term that is going to cancel the linearity when you average. And this is it's highly complicated memory term. You see, it depends on the functional derivative of the wave function with respect to the noise at past times. So it's like, how would the state have moved had I changed the noise in the past? Okay, that's a very twisted dynamical equation. Just, for example, it's impossible to numerically solve this explicitly just by doing a naive discretization scheme. There are ways to simulate it, but they are super indirect. Okay, and then the noise that enters here is just this time colored and not just a delta, as you would have for Markovian collapse models. Okay, and for a Markovian collapse model, this term would not be an integral and there would not be a functional derivative, and it would be a term proportional to a square, typically. So this is the starting point. And then you can check that if you average over the stochasticity, you get a density matrix that obeys a linear equation given by a non-Markovian CPTP map. And this is all thanks to this highly complicated memory term. This is just the first step of this construction. Okay, and then you have a trivial point, which is that now that you have this master equation, You can use a Stein spring-like construction to unitary dilate it, adding a bath of oscillators. And so it's fairly clear that you can always find a Hilbert space, a larger Hilbert space, on which all the predictions are going to be the same than if you had this description. Okay, so the weak equivalence is always sort of obvious and for free. Now, the second step in this construction is to normalize the state because it's not normalized. So you can check that this equation doesn't preserve the norm. And so the state loses all interpretation. So you just normalize it. But now what happens is that the normalized state does not give a linear master equation if you average over it. So you lost the very thing you struggled to get. And then what you do is that you do what's called cooking the noise. So you restore the linearity by continuously changing the law of the noise. So you're like, okay, taking expectation values still leaves non-linearities. Let me change the probability distribution so that it changes the expectation values so that they cancel away. And after, honestly, quite a lot of hard work, you can show that this transformation does the trick. But it's a highly non-trivial derivation, I would say. It's a full 2 pages to get this. And all of this is completely trivial in the Markovian case. So in the Markovian case, I think this is called Girsanov transform, and this is a one-liner, okay, in the Markovian case. This is really important. This is more difficult. And again, it depends on the whole history. So you change the noise depending on the whole history of the state. And at the end of the day, your collapse model is a normalized state, driven by this cooked noise. Okay, that's the output of your procedure. And then you say this stochastic state is like, what nature gives as the fundamental evolution. I can't write something more explicit. Okay, like this psi of the cooked noise normalized doesn't obey any simple equation. So you have to construct it this way. You define the linear one, you normalize it, you change the noise. And that's sort of the easiest way to get it, I would say. Okay, so just 2 salient points to remember is that these generic collapse models that people are now studying a lot in foundations are far more subtle than they seem. It's not just having a collapse model in which you put colored noise instead of white noise, which would be fairly reasonable. It is adding a complicated memory term in the evolution that is absolutely necessary for consistency, but extremely counterintuitive in terms of dynamics. It's very weird that nature would implement such dynamics. And you have also to redefine the noise field in a way that is maybe less horrible to write, but is highly non-trivial to derive. Again, how nature does that would be, of course, nature is allowed to be as complex as whatever, but this is really a more complex and counterintuitive dynamics than you would think. And importantly, the fact that these 2 things are non-intuitive will become very intuitive, or at least simpler, when you rewrite the whole thing as a de Broglie-Bohm theory. You can understand the memory term as a pure conditioning term in the Bohmian sense, and you can understand the noise dynamics, so the continuous redefinition of the noise, as the pilot wave equation in Bohmian mechanics. It's not just an approximate equivalence, it's really formally exactly the same. And let me try to explain you why that's the case. So I don't know if there are questions at this stage about these weird models that I want to...
I have a quick question, if that's okay.
Yes.
So you have an integral over the history. So
yes.
What defines 0 time then?
Yeah, you're right. So this is a big ambiguity in these models. So technically, probably for many, you're right. You should define a 0 time that's typically the origin of time and hope that your kernel here decays fast enough that basically you don't have insane non-Markovianity. That means you should need to know the state still till the beginning of time, but only in the few instances before. But I agree, this is the big issue of this approach.
Thank you.
Yeah. So yeah, I put 0 here. You could also have it run for -infinity. I just assume the time of the universe starts at a 0 here. But you know, if things are non-Markovian in a fully non-Markovian way, you always have to know all of the past to know how to evolve. The world is no longer a Cauchy problem where you can evolve from Cauchy surface to Cauchy surface. In a fully non-Markovian world, you need to know all the past. In fact, the Bohmian redefinition adds precisely the right amount of fields so that the non-Markovian evolution becomes Markovian on Cauchy surfaces. And that's why it's simpler in a way. That's why it doesn't have a memory term. Of course, it doesn't come from free. There is an extra space that sort of encodes this memory. Yeah, but I hope it becomes clear later. Okay, and now we are at the sort of last step of the construction, but I have to say not the easiest. I will really try to make so I will not do derivation, but really try to clarify what the objects are and what is equivalent to what. Okay, so now what I want to do, so I have this non-Markovian collapse model, and what I want to do is to find a Bohmian theory that is equivalent to it. The first step, which is easier, is just I want to find a bus such that if I couple it to the system, the unitary evolution on that bus, but tracing over the bus, is equivalent to the evolution of the collapse model where I average over the noise. Okay, that's to get the empirical equivalence, but fully explicitly. And it turns out using 100% standard constructions from open quantum system theory, it's doable. And the bus is the easiest you would think of. It's a bus of a continuum of harmonic oscillator. So you have oscillators that depend on the frequency, and you have a continuum of them for each frequency. And the bus is like the kind of frequency proportional energy plus, and then a coupling with sort of arbitrary coefficients to this, to the momentum of the oscillators. And then you can relate the 2-point function of the noise to the coupling these oscillators have with the main system. Okay, so that's the link between the two. And it's easy to show that for whatever noise, you can cook up these couplings such that these two functions are equal, okay? So basically the noise 2-point function is equivalent to the root of the Fourier transform of the couplings. And this is proved using Wick's theorem. Okay, so it's not, I would say, not a crazy difficult proof. And I think intuitively one can always imagine, okay, if you have something driven by complicated noise that has a legitimate master equation, then if it has a legitimate non-Markovian master equation, I can probably easily find a bosonic bus that would give the same results. And in fact, we just do it explicitly. So that's the weak inclusion. That's at the empirical level, we couldn't make the difference in the statistics we see. But of course, I still have a stochastic model, the stochastic collapse model, and this would be a fully unitary evolution. So the states of the system is completely different, even though empirically we can't tell the difference. Okay, this is a technical subtlety that I should say. In everything, in what comes, I will lie and pretend that I do Bohmian mechanics for these oscillators X and P. But that's a lie. If you look at the paper, I have to do first go into the interaction representation of the bus, then change of oscillator variables, but to get variables that are still canonically conjugated, so they are still legitimate oscillators. It's really a technicality. It's because in these new oscillators, the Hamiltonian looks horrible. And so it's harder to explain things, but you have technically, if you really want to recover the right Bohmian description, you have to do this transformation. It's hard to explain here. It's really a technical matter so that the two match exactly and not approximately. Okay, So now we are going to try to reproduce the collapse equations. And the first step is to condition on the Bohmian position. So what I'm saying is that now I take the state on the system plus bus. So the initial system, which can be whatever, typically that's our universe with a standard model, for example. And these bus are these, if you like, hidden harmonic oscillators. And now what I do is instead of having the full state evolving, I still keep on evolving, but at each step, I look at the wave function with fixed particle positions in B. So instead, I look at the state of the system conditioned on fixed bus positions. So it's now, this object is a wave function for the system only, and it's defined just by taking the system plus bus and fixing xb. Okay. Equivalently, if you like the ket notation, it's like taking the full state and projecting on xb on the left side. This is the same. And now you observe one thing is that you can write, it's a bit weird, but you can try to write a differential equation for this object. And what you realize is that it obeys exactly the same differential equation as the linear wave function in the collapse model before we do all the cooking and normalization. Of course, this object is fully deterministic. And when I say it obeys the same differential equation, it's true if you replace the colored noise by this object, by a fully deterministic function of the positions of the particle position in the bus, which I again took to be fixed. So they are deterministic, static, and the time dependence comes only through a Fourier transform. Okay. So this is non-trivial. You have to write it down. I'm sorry, I'm skipping it, but I just want to, this is the take home of the first step, that if you fix the particle position of the bus, then it looks like it evolves like a collapse equation, except with a sort of frozen noise. No, so with the noise coming from frozen variables, but the noise is still dynamical because of they are sine and cos omega t. And then what is insane is that now if you, this particle position, these Bohmian positions of the bus, if you take them, so if you take the full state initially as a product state with the bus, and if so at the origin of time, we come again to this issue of the origin of time. And if you draw the initial variables of the bus from the Born rule, then this state, which is a fully deterministic function of this particle position, has the same law as the noise in the collapse model before cooking. So this object that is sure deterministic, but it has some randomness in these initial conditions here. And in fact, when you look at it, this randomness gives exactly the same statistical law than the noise in the collapse model. Putting the two together, it means that if you look at this object, so conditioning on the bus particle positions, you evolve exactly like the linear equation with the same stochastic appearance that you would get. That's the first part of the equivalence. And the second step is where we add Bohmian mechanics. So, okay, right now I was conditioning on particle positions. I wasn't putting any Bohmian mechanics. Now, instead of conditioning on xb fixed, which is what I was doing before, I now condition on xb, the bus positions evolving according to their Bohmian dynamics. So I use the standard guiding law of Bohmian mechanics to guide the particle positions with a velocity field obtained typically from the phase of the wave function. I use the canonical method to do it. So now I have a new state, a new conditional wave function that depends on this continuously moving bus particle position of the bus. Bohmian position, sorry, of the bus. And what you observe from this is that this field I defined before, now it has sort of two time dependencies, the fact that these Bohmian particles are moving and the fact that there is this time dependence on the cos and sine omega t. But at the end of the day, you can show that the new field with this new time dependence is connected with the previous one in the same way the noise before cooking and after cooking are related in the collapse model. So the new field is related to the previous one with this equation. And this is exactly the same relation as the one connecting the two noises in the collapse model. And since the first had the same law, it means now they also have the same law. Okay, this new weird function of the bass positions has exactly the same law as the cooked noise. Okay, that's a technical subtlety. If I'm just standard Bohmian mechanics gives this rule for the velocity field of particles, you have to use a slight generalization to allow for more general Hilbert spaces, because here it's not exactly L2 of R. But honestly, this is completely standard, doesn't change anything. Just to not say anything that is technically speaking incorrect. And now let me conclude on all this Bohmianization stuff and what is sort of the result. So now, if we have the wave function on the system plus bass where we fix bass particles, it has the same dynamics as the linear states, provided this deterministic field we see in the equation, we take it to be the same as the noise. But lucky us, if we take the Bohmian positions of the bass, initially you draw them from the Born rule, which is the case at equilibrium in the Broglie-Bohm, then this field has the same stochastic law as the noise in the collapse model. And finally, if you let the bass particle evolve according to the standard Bohmian guiding laws, this transforms the field appearing in the equation in the same way that cooking, this is, sorry, written in an awful way, changes the collapse field. So if you do put these three things together, you get the strong result that I claim, which is that the wave function of the system that you obtain by fixing the bass positions to their real-time de Broglie value, it's a stochastic process, because there is some randomness coming from the Born rule. And this stochastic process, this wave function, this Bohmian conditional wave function, it would be called, has the same law, the exact same stochastic law as the wave function of the collapse model we started from, the one we wanted to reproduce. And furthermore, the law of the field driving this equation, which is a linear function of the Bohmian position, is the same law as the law of the Cook noise in the full collapse models. So it seems included in the first one. I mention it because in some cases people like the metaphysics to lie in the Bohmian positions and in the noise or collapse event in the collapse models. So if you want to show the ontological equivalence, you have to show more than the equivalence of the wave function. And so if you care about this kind of ontological precision, then you also need the second statement. Okay, so that is, I would like to insist really a much stronger result. Like I'm saying that the stochastic process of the wave function before averaging is the same in both cases after this construction. And so this shows an inclusion that all these non-Markovian collapse models you can reproduce exactly as Bohmian theories on a bigger space. Doesn't prove the other way, that every Bohmian theory you can rewrite as a collapse model. That's not true. Okay. Let me discuss, and this is where it will randomly switch to French because I forgot to translate all. So let me just say some implications of the weak results that I think are fairly straightforward, but are always blurred in the community. And the first statement is that collapse models make different predictions from standard quantum mechanics. And I think this is not true, or at least very misleading. The predictions differ only from a specific instance of quantum mechanics, the standard model. But you can always change the matter content of quantum mechanics to reproduce a given collapse model. So there is no way, no experimental signatures that you will see of a collapse model that is fundamentally different from just having a different Hamiltonian. Maybe it's a very weird Hamiltonian for some hidden dark sector, but still it would be reproducible unitarily, technically. And usually people say, oh, but there is some intrinsic randomness of collapse models. There is kind of this pure classical noise in them, so it gives specific signature. And the answer is no. Like this randomness that they have is completely empirically undistinguishable from standard randomness coming from unknown degrees of freedom. And at least our Bohmian predictions, our Bohmian construction is another way to see it, but you only need the weak equivalence to see that. Then maybe final point, then if you have that, then collapse models bring nothing to foundations. And there, I don't think so, because they do bring something. They solve the measurement problem. Okay, I messed up. I meant which is not an empirical problem. Okay, so because it's the measurement problem is more a metaphysical or an ontological problem. I don't mean that in any negative way at all. So for me, that's actually positive. But it's not empirical, so there is no contradiction that collapse models bring something, but that they are, in a way, the answer is no to the first two. Okay, this is where it switches to French, and I will translate. So the implications of the strong result and the ontological inclusion is that if you have some random dynamics and some deterministic dynamics, they can be fully equivalent. So here I have a Bohmian description, which is deterministic, but all the uncertainty is in the initial condition. And I have a fully sort of collapse model where the randomness is released progressively in time. But these are the same stochastic processes. That is, all the measurement I could make on them, even not measurement in the sense of quantum mechanics, really measurement like I plot the quantum trajectories on a computer, they would be impossible to distinguish. However, the difference is what's called nomological, in the sense that the law, the way you write the law, in the probabilistic sense, the filtration is different. But the stochastic processes are the same. It's the filtration of the information, the way randomness is released that is different. So this is really a subtle point. I mean, we can probably discuss it later if you're interested. Another point is that for this general collapse model, the dynamics is, I think, far more intuitive and plausible in its Bohmian formulation. And probably this means that we should restrict the name collapse model or the field of collapse model to Markovian models like GRW. Because for Markovian models, the construction I did can still be done, but it's super non-parsimonious, and then the standard collapse model description is orders of magnitude simpler. And so they are still interesting, but I think once we go into the non-Markovian case, it becomes much less interesting to have collapse models because of this Bohmian reformulation that is, in my opinion, far simple and fully equivalent. And of course, it's tempting to reproduce a construction we just did to existing baths in nature, like photons. And if you do the partial de Broglie-Bohm description of these, then you see that it's equivalent to stochastically unraveling the sector. And so it's a nice way to sort of hide the collapse model or hide the collapsing description within degrees of freedom that already exist in nature, instead of having a new bath. And if you do that, you can see it either in a de Broglie-Bohm way, which actually people had done before without realizing it was the same, or in the collapse model way. Sorry. And then my conclusion, and the point that I think was striking for Howard and I, is that we started from two completely different philosophies to create a single world for quantum mechanics, a single realistic world without any kind of subjectivity. Two completely different philosophies. And then we discover, after some hard work, that in fact, they do the same thing. Inside, in a hidden way, they do a guiding equation. And in the collapse model, it's very hidden. There is this cooking of the noise, but formally, the cooking of the noise is just a guiding equation. And so it seems interesting that so far, no one has managed to, okay, I exaggerate if I say no one, but no big leading approach has managed to have a single world emerge from quantum mechanics in a undoubtedly consistent way without resorting to some kind of guiding law. The only convincing and approach that I would like is what people like Adrian Kent have tried, where you do some conditioning from the future of the evolution to create behables in the past. And this is clearly not equivalent to guiding laws, at least I don't see any way to do it, and seems to also give a single realistic world. But I think there is a real challenge to find things that are consistent, that may be consistent with bound rules and things like that, and will not in a very convoluted way hide some guiding law principles, some pilot wave principle. And with this, I think I conclude. And thank you very much for your attention.
Okay, thank you, Antoine. We have questions here in the seminar room to start with.
I have a question, if that's okay.
Go ahead.
So Antoine, I'd like to ask about the bath.
Yes.
Could we maybe go back to one of the slides?
Sure. Let me go back to the bath definition. This, right?
Yeah. So we have a continuum of harmonic oscillators, yes?
Yes.
So is this formally equivalent to a quantum field?
Yeah, so here it's all non-relativistic, but yeah, you could see that as a kind of...
It looks to me like
it's a toy QFT, if you like, yeah.
Yeah. So, and then you attribute to that a particle position, a de Broglie-Bohm style position.
Yes, so each oscillator has a position, which in the QFT picture would be equivalent to giving reality to hidden variables to the field variable.
Okay, I see. I was wondering what space that particle position lived in, and I guess it would be a field configuration.
Yeah, it's very abstract. Okay, because we use it's infinite in frequency space, but you could imagine this frequency come from some localization in space. Okay, we are here working with a very abstract model in the sense that the indices J here refer to the whatever collapse operator. So whatever operator we collapse. Could even be that we are collapsing a single qubit, with sigma z. So J would be the index relating to the AJ corresponding to sigma z of a qubit. Or it could be something more complicated related to position, in which case this would have indices corresponding to position and frequency, and then it would really be super close to a quantum field.
Okay, thank you.
I have a question, Antoine.
Yes.
Firstly, thanks for the great talk.
Thank you.
I want to ask about the guiding equation.
Yes.
So you use the standard de Broglie-Bohm velocity field.
Yes.
Now, in pilot wave theory, we can add a divergence-free current, and that makes no difference to the continuity equation. So the pilot wave predictions are the same.
Yes, you're right. Yeah.
But does it change anything in the collapse model?
I think it gives, in the same way, like a different unraveling, but this, so it would give a different collapse model, maybe in one that is not as tight, for example, in terms of, decoherence collapse trade-off. But yeah, I use the one without the divergence, so without adding an arbitrary. We did not exploit this freedom.
I see.
But you're right. So I'm not sure. The honest answer is I don't know what happens if you try to use this generality. Does it buy you more general collapse models, for example, than the one we considered? That's possible. Basically, with this, we can match everything that has been proposed in the literature, as far as I know. But then people are creative, so maybe they will find something that doesn't fall into this reconstruction. In which case, we might need to use to add these terms.
Yeah, maybe if someone spins up a new collapse model, you can make sure that a different guidance equation also captures that. But on one side, you don't have any invariance in the results, in the empirical predictions, by changing the guiding velocity. So I would expect that you would not also have, on the other side, in the collapse models, any difference in empirical predictions.
No, of course not. But all these predictions are, all these predictions, in a way, are just at the level of the unitary evolution with the bass, or at the level of the average equation for the collapse model.
Mhm.
You don't even need Bohmian mechanics for empirical equivalence.
Yeah. Okay, thank you.
But I think it's important in the field to show that you go beyond that, because of course the empirical aspect is not all, because otherwise you wouldn't really be doing quantum foundations anyway. I mean, you care about a bit more than that probably.
Okay, thanks. Yeah.
All right, other questions from the Zoom participants? All right, seeing none, let's thank Antoine again for this nice talk, and hope to see you in person sometime soon.
Yeah, thanks a lot. Thanks a lot for your attention and for having me. Okay, have a good day.